Okay, good morning everyone, and welcome to the 2020 edition of the Royal Tyrrell Museum Speaker Series. Today, the Royal Tyrrell Museum and its Cooperating Society are proud to present Dr. Jenni Scott. Jenni is an associate professor in the Department of Geology at Mount Royal University in Calgary. Jenni is originally from Regina in Saskatchewan. She obtained all of her degrees at the University of Saskatchewan in Saskatoon. For her undergraduate thesis, Jenni studied dinosaur and bird footprints from the late Cretaceous Dunvegan Formation of northern Alberta. For her master's thesis, she studied modern and Pleistocene trace fossils and their taphonomy in the Kenya Rift Valley of East Africa. And for her PhD, Jenni studied the composition and distribution of trace fossils in the Saline Lake basins of Kenya and the Eocene Green River Formation of Wyoming. After completing her PhD, Jenni moved to Edmonton to do a postdoctoral fellowship at the University of Alberta, where she studied trace fossils from the Dinosaur Park Formation in Dinosaur Provincial Park. She was subsequently hired as a faculty member by Mount Royal University, where she still is to this day. Jenni's research interests include using detailed sedimentology and trace fossils to interpret the stratigraphic packaging of rocks in lake basins and marginal marine environments. These days, she's studying 3 million-year-old deposits from Kenya to learn about changing environments associated with early hominid evolution and the onset of northern hemisphere glaciations. She is also studying deposits of the late Cretaceous Brazo Formation in the foothills of Alberta. Today, Jenni will present an overview of the work she has conducted in Dinosaur Provincial Park. So without further delay, I present you Dr. Jenni Scott.
Hi, everyone. Well, thanks very much for having me. It's really nice to be on this stage. What a beautiful auditorium, and thanks for coming, everyone. Good to see your faces out there. I'm happy to be here to know a little bit about what I've been thinking about and what I've been working on since about 2012. I started working in Dinosaur Provincial Park. So this is a photo of one of my favorite photos of one of my favorite places in the park, and I love it because you can see in the Badland weathering, it's very complicated in terms of basically the light gray and the dark gray. That's the sand and the mud. And so my goal in this place is to try and start to find some patterns in how those layers match out through time and what they can tell us about changing environments in that area. And so more specifically, this talk will be about trace fossils, but also the study of the sedimentology. So looking at the details of the rocks and how they stack vertically. That's the stratigraphy part, the strata part, in the Dinosaur Park Formation. And it turns out that maybe some of these observations and our interpretations of the environments as they change through time might have something to do with dinosaur evolution and assemblages of dinosaur fossils. So I'm a geologist here, so I'll show you a figure here and there of the dinosaur biostratigraphy and talk about that a little bit. But my main role is to interpret the rocks and see what's happening with the environments as they change through time. I need to thank some I've had several students working with me on this, but in particular, Rita Aslam, Taya Weinberg-Hensler, and those are two students that really contributed to this work. And so a lot of the figures incorporate their work as well. And Doug Stewart is a colleague from Husky Energy that did a lot of this work with me as well on the stratigraphy and studying the rocks. So I just wanted to thank those guys up front because it's basically their talk as well. So where are we? Hopefully most of you have been to Dinosaur Park before. It is not in Drumheller, but since you're in Drumheller, you probably know that. A lot of people get the places confused because they look similar, but the rocks are actually a little bit different age. And so we're talking about Dinosaur Park. Okay, so that's the blue dot there. And some of the other evidence that I'll refer to today for interpreting the environments come from a drill core in the subsurface from Strathmore. Okay, so everybody probably knows the town of Strathmore. There's a core right near the park called the Princess Core, and then Medicine Hat and Brooks are on here just for reference. Okay, so why do we love this place? Because the outcrops are just spectacular. So the outcrops are good around here too, okay, I find they're great. But Dinosaur Park is just unreal, in part because it's a little bit more 3D. So we've got all sorts of variety in the exposure. We can see just individual beds. You can trace, that we can go along the valley floor here and walk around the same bed. Or in some places, as I'll show you some pictures of in a while, we have some also pretty steep cliffs, so that looks a lot more similar to this area. And so what you're looking at in this image is the two main formations that make up the bulk of the rocks exposed in Dinosaur Park. And so this talk is going to be focused on the upper stuff. That's the Dinosaur Park Formation. And so right at the base is where we have an older one called the Old Man Formation. So I'll show you a figure so that you see where that fits in the bigger picture. But for the most part, we'll be talking about the rocks above that. Okay, so what was it like there? This place is interpreted to be a coastal plain in the Cretaceous. So the plain is beside the coast, and the coast is the margin of the Cretaceous Interior Seaway. So we're very close to the shoreline, although we don't know exactly how close. And that is in part because the shoreline was, of course, moving back and forth through time. And so that's something that characterizes coastal plain settings, is that they're back and forth between more on the fluvial or riverine environments, and then also the coastal environment. So every once in a while, the shoreline will move landward, and we'll get water everywhere. So it's really important to consider that the environments are changing pretty much constantly through time. And so the scale on this example is much different, probably, than the Dinosaur Park Formation, but it's interesting to illustrate what is a coastal plain. And so it's one of the ones that's known fairly well. So this is the Mississippi River coming down here into the Gulf of Mexico, and that's the main lobe of the Mississippi River Delta. So that is a huge system with lots of sand and big rivers. The part that's off to the side here, this is where there used to be a river coming and feeding a delta, but it's been essentially abandoned. And so in this place, this is where the water level is actually rising in that area. And so you've got large swamps and wetlands all across this whole area right here. This is known as the Atchafalaya Basin. And so it's close to the Mississippi, where there's rivers coming in and deltas building out, but it's also getting flooded out. You may have heard that sea level is rising today, and it is globally, but not everywhere. So in places where there's a lot of sand coming out, like the Mississippi, the delta can still be building forward. But most of our environments that we get when sea level rises are a little bit more like the Atchafalaya instead. And so that compares a bit better with what we see at Dinosaur Park. The other thing we see at Dinosaur Park is many, well, I don't know a number, but it's thousands. It's an unimaginable number of meandering river systems that make up most of the rocks in the Dinosaur Park Formation. And so just to give you an idea of what those are like, this is upstream on the Mississippi River. So we actually had it in the top of the last figure. And you can see that the channels are going all over the place here. We can see some lines. Those lines along the main channel are showing us where the channel used to be. And it shows us that it's always changing. So this is the main Mississippi Channel now, and this is more on the Atchafalaya side. This little figure up in the top there is also just to illustrate what happens as these point bars in meandering rivers expand and they migrate, and they're always switching in their position, which of course makes the rocks and the sediments very complicated. Okay, so for our purposes, just get a picture of this kind of place plus that fluvial stuff in your mind, because this is more or less the environments that we'll be talking about. Okay, so that's the environment setup. Now what about the dinosaur biostratigraphy? So this is a figure that my student Thea Weinberg-Hensler, when she was working with me at Mount Royal, she put this together. And so we were using the work of other people, of course, because we weren't the ones working on the bones ourselves. And so she plotted out the horizons defined by a couple of different authors, so Mallon and Ryan and Evans. And what they recognized is that if we look at how the dinosaur species stack through time, we've got basically timelines where we see more rapid turnover in the species. And so this is what we do for biostratigraphy. Maybe you've heard that word before, or maybe you haven't. But essentially, if we have time, or in this case, we have thickness of the Dinosaur Park Formation on the left, and we put the ranges for all of the different types of dinosaurs. The important part to get out of here is that at certain points we see 3 of them appear at the same time as 2 of them disappear. And so we're just looking for these places to correlate change. And that's what's meant by this turnover. Okay, so these turnover events are slightly different depending on which author you're reading, but we wanted to investigate if those turnover events could be in any way related to the environments that we see in the dinosaur park formation and how those change vertically through time. So we wanted to establish if there's a link between these things. Based on some work I had already done before working with Thea, I had some guesses. Well, there's these kind of horizons. I wonder if they mean something in terms of the dinosaur biostratigraphy. Do they correlate? And so we go back to the rocks. And so I'll give you just a little bit more intro about what this place is like. So in the Cretaceous, we of course had the mountains building on the west here. And the sediment was coming off of the mountains, building these big wedges. At the same time, of course, we have the Cretaceous Seaway. And so when we get mountains building, one of the things that happens, in this figure on the left, what you can see, is you essentially get, you don't have to worry about all the words, of course, but just the picture. So when the mountains come up, they produce a heavy load, and that load deforms the crust of the earth, and it creates a low. And in that low, you can get seawater flooding as long as sea level is high enough outside of that position. And so that's exactly what happened here. So the mountains were forming, they created the load, and it caused the crust to kind of sink down beside them. So the ocean came in and filled the spot. And so for our case, this is about our time period that we're talking about. This is the Cretaceous Interior Seaway, about 75 million years ago or so. And so we see the patterns in the flooding changes as the mountains are building. And then finally by 65, the mountains are not as actively building a load and deforming the crust. So sediment starts to fill it in, and that's kind of the end of that. Okay, so that's kind of the big scale background of what we're talking about. In terms of all of the different formations that we get, we can see that the brown here is just representing the Cretaceous Interior Seaway, and the white is representing all that, the clastic wedge or all the sediment that's coming off of the mountains. And so where we are is we're kind of right in here. There's Dinosaur Park, and it's at the top of where we get kind of our last main flooding event of the Cretaceous Interior Seaway. Sure, there's some mud up here, but this was the main one, the main last one, and that's the Bear Paw. So the Dinosaur Park formation then was deposited during this period of overall sea level rise. In theory, we expect that there's going to be pulses as the sea level rise at different scales. So it could be controlled by climate, it could be controlled by changing amounts of sediment coming into the basin, or maybe even thrusting events in the mountains. We don't know exactly what's controlling it, but there are pulses of water coming in and water coming out through time. In that case, what we expect to see in the sediments is changes between basically the proportion of sand to the proportion of mud. And we can kind of keep it as simple as that. You will see some pictures of environments that are more complex because they have mixed sand and mud. But basically, those are our only 3 options. Lots of mud, lots of sand, a mix. So we expect to see more sand representing the rivers when the sea level is low, and we expect to see more mud when the sea level is high. And so this is redrawn from one of Dave Eberth, who I think he actually did finally retire this year. Is it true? Maybe you guys know him. Dave is great, and I should really acknowledge him right now as well. He definitely contributed to my thinking and worked with me quite a bit in the field. So this is redrawn from one of Dave's beautiful figures that shows us what that whole wedge, in our case our clastic wedge, looks like from Alberta to Saskatchewan. And so one of the reasons I wanted to show you this little bit more detailed version is because we've got back and forth, 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 and so on again. So first we have the wedge building out, and then we have the wedge being flooded again by the Bear Paw above. And all along the while, we see evidence of more sand, more mud, back and forth. And so we do see that there are these pulses of sea level rise and fall. Okay, so how are we going to pick this out in the rocks? Remember that we're talking about the coastal plain. It's got all those meandering rivers, and they're moving around. And inside, the sediments of those deposits are very complicated, and they're constantly changing. So how will we piece it together? How can we actually see whether or not we've got more sand versus more mud when it's all a big mix to begin with? And so it is pretty tricky. And so just to give you a sense of how tricky and what the sediments look like, don't worry too much about the words here, but this is one of the localities in Dinosaur Park that I call amphitheater, and so do the other geologists, but apparently the parks people don't call this amphitheater. Anyway, that's our locality, we call that. And what we see is we've got a couple of big stripe of sand at the top, so that kind of light gray color, that's the sand, and that represents the rivers. Below, we've got mostly sand. That pink line means the Old Man's Formation is below it, so we're at the base of the Dinosaur Park here. We've got some mixed mud and sand. Okay, so that's the point bar moving around. And then we've got some big blobs of mud. And that's what happens if the channel gets abandoned and switches somewhere else. Okay, well, we go somewhere else. We've got a lot more mud. The mud cuts the sand. We've got basically the stripy stuff. So that's the sand and mud representing the point bars. We've got lots of mud representing a little channel that's filled with mud. And then again, we've got sand everywhere in this big horizon. So this horizon is actually the same one that we saw in the previous photo. And so sure enough, we start to see like we do have patterns. As long as we can start to see through the complexity, there are patterns and, you know, continuous sands that are, you can see laterally in that area, and continuous muds in that area. The sands are particularly easy to see, but this is basically the mess you're looking at. Okay, so trying to piece that together in a system where you've got all sorts of fluctuating grain sizes in the sediments, it can be fairly tricky. Okay, so how to figure this out? We need to map and we need to do stratigraphy. So we have to start by measuring those rocks to see how thick are each of the units, and then start connecting the dots. Okay, so that connecting the dots between different places where you measure, that's called correlation. And essentially what we're doing when we're correlating is we are mapping timelines across the area. And so we can map using stratigraphy, and we can also understand how environments change using stratigraphy. Back to looking for evidence of the sea level. Again, we should have widespread evidence of more mud everywhere if sea level actually came up. And we should see more sand if sea level was lower. So here's some of the localities that we work. So there's the main part of the core, or the park preserve. I always call it the core. I've been scolded for that. But the park preserve area, maybe some of you have visited that area. It's spectacular. Anyway, so there's several localities we've looked at there. And then out by Idasley is also an awesome place. And so studied a few places there. On the north side of the river, I called this Moose Face because it's basically a cliff and a moose lives there, so I called it Moose Face. And Happy Jacks, which maybe some of you guys have heard of Happy Jacks too, I'm not sure. Good place. And then there's some areas in Steveville, which we've also looked at. And so that's most of the localities that I've worked trying to piece this together. There's a couple others that are further away, plus there's that Strathmore core, but for the most part, it's outcrop based in the park. And so to measure the sections, this one was a really fun one. This is Moose Face. And so this big wall that you're looking at here, that's the face. It's just spectacular. You have to walk around and try and find these sections. And then eventually you'll find one that's fairly continuous. And this one is great because it goes all the way from the bottom. So it's got the Old Man at the bottom. Goes all the way through the Dinosaur Park. Up to the Lethbridge Coal Zone, which is the black line at the top. And then finally to the Bear Pass. We've got the whole formation in one viewpoint. That's impressive. And so the little blue line that you can see, that's the path we took when we measured this section. And so some students came out and helped me do that, and it took a few days. And we collected gamma ray data for it and took all sorts of observations and samples and such. So we did that in most of those localities you saw the dots for on the park. And the other thing we were looking for is trace fossils. Okay, so Francois mentioned that I did my undergrad on trace fossils. Those were vertebrate ones of dinosaurs and birds. But I also study trace fossils that are produced by worms, insects, whatever. Whatever it is, as long as it produces a burrow or a footprint, I care about it. because the environments give us, the trace fossils give us clues about the conditions in the environment. In our case, if we're trying to recognize when is the sea level coming in and out, we want to see evidence of changing chemistry in the water. So we want to be able to try and see if we're going from fresh water to marine water or somewhere in the middle. And so just to give you a little bit of background on this cool figure, this is from a professor from University of Alberta named George Pemberton. Actually recently died. I think it was actually just last year still, or maybe the year before now. So George Pemberton is a pioneer in this work, and along with his students and colleagues, what he recognized is that there are patterns that we can see repeatedly through time using different types of burrows and traces that animals of any sort make. And so this particular figure is showing it for marine environments. And so the shoreline would be way up on the left. And so we know if we're dealing with the coastal plain to the fluvial or river side of the story, we're a little bit off the chart. But basically, as you get more and more marine, the more and more diversity you see with the trace fossils. They change in their assemblage, and they also change in their size, and there's all sorts of details you can get into. But for the most part, we see that as we go marine, we get a higher diversity. And so in the environments we're talking about, we're actually in a very low diversity zone. But we did find some when we were measuring those sections and trying to figure out where is this evidence for maybe some more saline waters. Well, sure enough, as we might predict, they're going to be up at the top of the dinosaur park, because that's when it's almost flooded out by the Bear Paw Sea. And so that's exactly where we saw them. And so these are just some images from the outcrop in Dinosaur Park of the upper part of this section. And so in this image right here, what you see is there's a big mud-filled channel, and then the very top of prairie level, that's basically representing the flooding of the Bear Paw right up at the top. And so in that zone, the same area, if we look to the right now, a little bit closer, we see we've got the Lethbridge Coal Zone, that big mud-filled channel, and then Bear Paw coming in at the top. Now the sand and mud that you see here, this is from the point bar that's accreting laterally as it moved around below the Lethbridge Coal Zone. And if we look on the eastern side of the park, so this is over by that Moose Face section, here's the Lethbridge Coal Zone again. We see another mudstone layer that's persistent across a large area. And then in terms of what we've got, lots of sand and lots of mud. And it's up in this area here that we get most of the trace fossils. And similarly in this area, it's mostly right in this zone. Okay, so we expect that this is going to be the place where we start to pick up on some marine waters. Okay, and just to give you an idea of what it looks like there. So even above the Lethbridge Coal Zone, which is this black line here, and the same black line there. This photo on the lower left is just a close-up of the one that's above. Above it, what we see, there's still channels, but we have the mixed sand and mud, and then lots of mud. And so in that zone again, that's exactly where the sea level is coming in. But the rocks look almost the same as the stuff that's below that level. It's just the trace fossils that give us the evidence that we start to have brackish or marine water influencing the environments. And so this is a very busy figure, I realize, so don't worry about reading it, but just note that beside the columns, okay, we've got Lethbridge Coal Zone marked across the different columns. All of these words right here, those represent different trace fossils that we see. And so they're all pretty much grouped just below and above the Lethbridge Coal Zone. So right at that area where the flooding starts to happen. So from our study of the sediments and the trace fossils, this is just a cartoon interpretation of what we think the environments were looking like at the top of the dinosaur park. And so in some places we've got a green sand that represents this barrier bar here with lots of mud behind it. And in other places we've got more active channels, but it looks like they have some brackish water in them. And that's based on the trace fossils, because it's the traces that are giving us the clues to the chemistry. The sedimentology looks almost the same above and below. So in this figure, we'll look at the pictures here a little closer in a moment. But basically what we see is on this side we've got number 1, and on this side we've got number 5. And if we go back to our map here, you'll see that 1 is the most fluvial, okay? And number 5 is basically the most marine. So let's just look at some pictures of what we were finding. To tell you the truth, we're not finding too many of them because for the most part, this is a landward kind of place with lots of fresh water around. But nevertheless, we found some. If we start over number 1, nothing, just pictures of the sediments themselves. If we move into the brackish fluvial estuarine channels, we start to pick up on some tiny little burrows. So wherever you see 2 letters and then an arrow, it's pointing at a burrow of some sort. As we get into the environments that are above the Lethbridge coal zone, and we're getting that much closer to the ocean coming in, or the sea coming in, we start to see bigger traces like this, and they are filled with sand, and they're produced in mud. And then as we get to the very top, this is that green sand of the barrier bar, and we actually get this type of trace fossil right here is about this big, and that's kind of like a bunch of branches that are coming out, and it's produced by a marine polychaete organism, and it's big. So what we see is the increasing size in traces and also increasing diversity and increasing types that we saw in Pemberton's figure show us that we're in a marine environment. So that all makes sense. That's great. We'll just look at those a little bit closer. Okay, so there's the fluvial. Not much going on. Some evidence of brackish water from those simple traces. A little bit more evidence of brackish water, increasing salinity in this case. And we also have features like this cineresis crack that start to show up at the same time, which forms when you get mixed saline and fresh water. And on this side then, we've got the largest, most marine type of trace fossils. Okay, so one thing we see is at least it works, and we were able to predict that, fine, the top is going to have traces and give us some clues. And this is that green sand at the top. This is the one that's basically totally marine, and we're way up here, just at prairie level. Okay, are there other clues about sea level pulses coming in and out of the dinosaur park? And so the sedimentology is complex. We don't expect to find much for trace fossils, but nevertheless, we did find some. And so I will show you a couple of examples. It's pretty scrappy, and so here and there you can find some. The trick is being able to predict where you're going to find them. And sure enough, the patterns are starting to emerge as we get a few more examples to tell us, okay, we've got brackish water in different places of the dinosaur park formation, not just up at the top where we expect it. And so they're always in these mixed sand mud units or very muddy units. So we know that basically that lithology and as a whole, and if it's a mappable horizon of more mud, we associate that with a horizon that represents increasing sea level, even if we're a bit landward. So remember that picture of Atchafalaya Basin? It's a flat place with a lot of lagoons and swamplands. So we might be still on the landward side of the environments, but when the water level comes up, it floods out everywhere. And so you get variability in what your environments are, but they're all muddy. And so the places we're finding the traces are in the mixed stuff from channels, but mostly mud. And so here's some pictures of some simple ones right there. It's just those sand-filled features that are produced in the mud. And so those are biological. Even if we're unable to name these things, some of them I can name, like this one I call Tychicnus, this one is Gyrolithes, whatever the name is, doesn't really matter too much. Even if we can't name them, one thing we know is that in completely freshwater channels, we really expect to find pretty much nothing for trace fossils. One locality at Happy Jacks, we found some. That was kind of low down in the dinosaur park. At the boat, this is moving up a little bit higher. And so sure enough, in a similar horizon. So here what we have is a coaly horizon, this kind of purplish color. There's a lot of plant material in there. And so that would be more of the overbank or swampy type of setting. But we get a channel coming in, and it's right at the base of that channel that we see the trace fossils. Okay, so in this particular picture, I know they're not overly convincing, but this horizon was where we found a lot of them, and they're right at the bottom of that channel. That's kind of right at the base where we've got a sharp change between lots of sand to lots of mud. Beeville, similar pattern. And so the burrows, again, there's just a simple one. It's always really in the clayey stuff, in the really mud. And so again, just an open burrow filled with sand, and it's into mud. Fine, so we're making these observations. Does the whole thing work? Well, okay, let's say we've got some examples, kind of spotty examples in the lower dinosaur park, some indication that we've got evidence of the sea level changing a little bit. Can we actually map horizons to show that this was a widespread event and real? And so this picture of me that Doug Stewart took, I have, it's not overly high tech to tell you the truth. It's a laser rangefinder, and it's got about 500 meters of range. And so I take a datum, so I pick a horizon, and then I measure the distance below it, and we basically start mapping out different horizons in the outcrop using this tool. Ideally, someday I'm going to have a drone, and we're going to make a drone model and connect the dots, and it'll be all perfect. But for now, our equipment is pretty basic. And so we actually go out there and walk around and try and find the right horizons to start mapping. Remember a while ago I said we got to learn to see through the complexity. And so we have to choose which of these horizons are probably going to give us the answer that we're trying to find. So we use the laser rangefinder, and we correlate certain horizons that we think represent this change in sea level. Like this one up on the top of the cathedral. So if you guys have been to Dinosaur Park before, you've probably seen this. It's massive and it's beautiful, and it's one of the places right near Valley of the Moon. A lot of people go to that particular spot in the park preserve. This horizon right there, turns out that one in particular, you can map around all over the place, and it's very distinctive. It's close to the top, so we know we're kind of in the right zone where we expect to see more marine, and sure enough, we can start to map that one. In terms of an interpretation for this unit, in the more detailed stratigraphy, which I'm not going to get into in this talk, what we can see is, you've probably noticed I've got some red dotted lines in a lot of these figures. Okay, so the red dotted line represents where the sea level was the lowest, essentially. Okay, and so we've got channel deposits above that. And the green and the blue lines represent when we interpret that the water level, base level / sea level was the highest. And so after looking at this in more detail, we basically cut the cathedral in half and say at this point, the channels were abundant and mappable across the area. And at this point, the mud was mappable across the area. So in this figure, this is the same figure I used on the first slide. What we see is there's the Lethbridge coal zone in the distance, and we've got this persistent mud bed in the foreground. Okay, so what you're looking at here is that these are the sections. They're very tiny, so I know you can't see the details, but the big orange and brown bars are there to help illustrate where we interpret we've got these mud-dominated horizons. Okay, so internally they're a little bit variable, but they're still mud-dominated, and so we can start to map them around. And sure enough, it actually correlates quite well from place to place. Now back to the dinosaur biostratigraphy part of this, one of our ideas and our questions was, okay, can we explain these turnover events in the dinosaurs by mapping out the stratigraphy and seeing how the environments are changing? Coming in with the hypothesis that sea level is going up and down all the while, and maybe we can map those events. And so in this figure, what you see, of course, you've got our pink and blue lines representing Malin et al. And Ryan and Evans turnover events in the dinosaur biostratigraphy. And when we put those, see, those are all measured above the Old Man Dinosaur Park contact, which is great for us because that's all we have to do to them, okay? So there's a margin of error of about 5 meters on each one of these lines. But basically, if we plot those lines above the Old Man Dinosaur Park contact, then what we see is we've got a rough correlation in most of them with the brown lines. It's a little bit up and down around it. Okay, so I've got some different ways to think about that and explain what's happening. But one thing we know is that every time those channels come back, they cut down and they cut out bits of the mud that once was there. So there's all sorts of evidence of that. You got a flat mud layer and a channel comes by, it cuts down into it. And so you actually remove some of the upper parts of the mudstones when the channels come back. The fossils are primarily at the bases of those sands because most of the bones in the bone beds are actually found, I'll say most, I mean a lot of them aren't, but a lot are, where the bones are actually in the bases of those channels. And so to kind of try and understand why doesn't this work perfectly, why doesn't it, but it works a bit, is that we have these different reasons for having air. And taking into account the complexity in the environments, I think actually it lines up pretty darn good. Okay, so remember we've had some trace fossils lower down, okay, not just up at the top. Well, does it work down there? Well, if we interpret what's happening with the pulses of sea level going up and down, let's just follow around the red line here. So underneath the red line, what we see is that this red line is actually cutting down, and so the sand is cutting out part of the mud. Underneath that, it's quite complex. And you'll see there's a blue line here. So that blue line, we interpret that blue line right there. Here it is again on this figure. We see really good trace fossils in that particular spot. And it makes sense. So I won't get into the details of all the stratigraphy stuff that we're thinking about here, but basically these different colors of the lines show us our interpretation of when we think there was basically the brackish water comes in on the blue line. The water level is the highest, or there's the most mud on the green line. And then the next time a channel comes back, it cuts it out, and that's this red line. So it's those types of settings that actually the other examples from the lower Dinosaur Park Formation start to basically sit in the same position in terms of our interpreted sea level rise and fall patterns. And so we're always finding the trace fossils along the blue line, essentially. Okay, so considering that we've seen this evidence for changing chemistry in the channels, changing environments that are mappable at least across the area of the Dinosaur Park and then to about 30 kilometers west of there at Matsawin Creek and into the Strathmore Core, we can say that it seems like these surfaces, the dotted lines, plus the sediments, so the mud versus the sand, are mappable horizons. And so what that means is we can interpret what's changing with the water level over that whole area. And so it seems that that also matches up fairly well with those turnover events in the dinosaur biostratigraphy. Okay, so that's the same figure. We already went through this one. What's going on with us? Okay, well, I haven't got into any details about the dinosaurs themselves because, as my disclaimer indicated, I'm a geologist. So I can't tell you much exactly about the behavior of each of the individual dinosaurs that were around, but one thing that we can see is those big changes in the assemblages might be representing different things going on in the environments. And then through that, we see that it's the environments that are potentially controlling what's happening with the dinosaur evolution, essentially, because that's what those turnover events represent. So what's some ideas about that? Okay, well, if all the environments changed and became wetter as the water levels rose, then most of those dinosaurs, their habitat and their environments is going to change, right? So they're going to move on to the place where it's what they want. If this is a new environment, especially if it's saline and essentially marine, they're going to be out of there. Okay, so the idea is that they move out. The mudstones, the sediments themselves, they're deposited more slowly than the sands for the most part. And so I think that they represent like a lull in time. And so we're basically having changing time scales as we look at the formation, the sand to muds, the sand to mud. So we've got more time wrapped up in those mud horizons. And then, as I already mentioned, the sandstones are erosional, so they remove more time from the record. And so what we see is it looks like it's rapid turnover. So you had 2 of those guys gone and 3 appear, all on the same line. It's not quite like that, because that's just how our evidence shows us it is, right? So the mud represents more time, and then time is removed in the sands above, and so it looks like everything is happening very quickly. Maybe it isn't. Okay, and so that's where the great work of David Eberth and others comes in for looking at the timing of all this, so we can start to figure out, are these changes in sea level even potentially controlled by climate? And does that have an influence on the sea level of the interior seaway? Those kind of questions, that's for future work. So that's this is what I've been working on in Dinosaur Park. And looking at the details, these are some of the more interesting and exciting ideas that I think we've come up with in terms of what this could mean to us. So thank you.